OK, so any leftover questions from the last talk before we move on? OK, so I want to talk about a nice special case of this theory of sheaves of categories. So it's the notion of a group action on a category. So it's a kind of analog of the notion of like representation of a finite group, usually. So of group representation. So for example, usually if you have g acting on x, that gives rise to g acting on functions on x. What this subject will give is if g acts on x, it'll give rise to g acting on d modules on x, where g acting on d modules of x is something that we need to define. So here's one way to give the definition. So let's define the category gcat. Well, not defined as, but read as category of dg categories acted on by g, and g is an affine algebraic group. So in my notes,
The side is also classified right now.
Yeah, right. It's not a definition; it's a pronunciation.
Sheaves of DG categories over DG?
Great, except I just want to use, so I'm going to make, so so Hinich suggests a perfectly adequate definition. I'm going to make a different convention and define it as sheaves of categories over BG de Rham. Again, the symbols commute. It's B of G de Rham, and it's BG de Rham.
This is not the same thing, right? Because that's not one affines.
It's not the same thing as what?
As being a module over D modules on BG.
Absolutely. So fact. Actually, well, I'll explain your point.
Oh.
Yeah. It was a fact that was stated. Dragos is very clever, so he's already figured it out without any explanation. But we'll spell it out now. So OK, so an analog here is that.
So do I understand correctly that we first take BG and then derive, or not G derived and then B?
Not derived, de Rham.
Derived, sorry.
The two commute. Yeah, you can't misinterpret the formula, or I would need parentheses. B in de Rham. Yes. OK, so an analog here is that, well, you can think a representation of G is the same thing as a quasi-coherent sheaf on BG. And by the same token, it's going to be way more boring, but a representation of G de Rham is the same thing as a quasi-coherent sheaf on BG de Rham. So usually, in the abelian categorical world, there are not so many interesting representations of G de Rham. There are interesting X's between them, as was discussed this morning. Because this is the category of D modules on BG. But this dictionary will still, yeah, so maybe it's better to say category acted on by G de Rham. I'm just going to limit the language and remove that de Rham. But this will be helpful for us in thinking about the translation between our intuitive notion of category acted on by G, and this more opaque notion of sheaf of categories on BG de Rham. So given C, a sheaf of categories over BG de Rham, the underlying category, let's say, is defined in the following way. So you take the map from the point to BG de Rham and pull back. It's a definition. This is spec K. So that's exactly an analogy with this picture, in which like when you're translating between representations of G and quasi-coherent sheaves on BG, the way you think like the vector space underlying your representation, that's the pullback to the point. Another thing you could do with a representation is you could take its global sections on BG itself. And what does that correspond to? Invariance. So here we're going to write C sub G for this is going to be global sections of BG de Rham with coefficients in our sheaf of categories. Let me even. Well,
A sheaf of categories, which is C, right?
Which is C. Yeah, maybe I should change the notation. I'll call this like that, or F. It's a sheaf. It's a bit of an abuse. So then I'll say the underlying category C is P upper star of F. So this thing, the first one, I tried to write C. It was a bad idea. Math, yeah, I think math frac C or something like that. Yeah,
Yeah, it's better.
yes, exactly. OK, so to spell out this, yes? F.
Sheaf is F, underline category C is pullback, and this is C to G. This is not F to G?
No, I want C to G. So OK. Sorry, I should have made better decisions about the notation. Let's reset the notation for a second. So I want to think about the notion of sheaf of categories on BG de Rham, as an analog of the notion of representation. So it'll be a richer notion than representation of G de Rham. We might as well think representation of G. So there are three different vector spaces, not vector spaces, three different linear algebra objects around in this picture. So one of them is the vector space of our representation. It's assumed everyone knows what that is. A second thing you can do is you can take invariance, and that gives you a second vector space. And a third thing you can do is think about a certain sheaf on BG, which is a kind of formal gadget. It's a quasi-coherent sheaf on BG. You can think of it, you can identify the category with rep G, but let's just think of it as a kind of abstract thing for a second. So here, F is my abstract thing, the sheaf of categories on BG de Rham, which we're taking as initial. So then we can think the underlying vector space or category of our sheaf of categories is what you obtain by pullback. So that's by analogy with this formalism. And then the third thing you can do is you can form the invariance category. And that corresponds to global sections of the sheaf. Push forward to the point. Or it's a certain right adjoint.
So this is as if you denoted by rho the representation V, the underlying vector space, and the invariance by V to the power of G?
Well, no one, yeah. Rho is usually kind of the homomorphism, right? In a first course on representation theory, you don't usually talk about quasi-coherent sheaves on BG, so there's not such good notation. Yes?
Do you have a notion of underlying category for other stuff than BG? So when you have like a sheaf of categories over something?
No, no. I mean, it's really using this particular covering by the point.
A module over a category, so you could imagine that there's an underlying category.
So you can always take the fiber at a point of your stack. And the nice thing about BG is, well, it's about as interesting a stack as you can get with a point. Yeah. OK, so an example is, let's say that G acts on some variety x. So in this case, we can form the stack x mod G. And we can take, well, take its duram, take the map down to point mod G duram, and, so to speak, push forward like, well, what should be written as quasi-co of the stack x mod G duram. So hopefully, OK, I'm explaining it in the formalism we've set up. We're going to set up a more convenient formalism in a minute. So this is our F, is like this formal gadget. So what is our C? So C is global sections of the point with coefficients in the pullback. So how do we compute that? So we take x mod G duram, mapping to point mod G duram, and then we take the fiber product over the point, and then take, and then what we get here is just x duram. Cartesian square, yeah. Is that how you write it? So push, pull should be the same as pull, push, if there's any justice in the world. And that's saying that the underlying category is d of x. And what we could do instead is we could take global sections on point mod G duram, and that corresponds to push forward, push forward. So that's going to be the category of d modules on x mod G. So it allows us to write formulas. To write a formula like d of x to the g is equal to d of x mod g. OK, so here's a second picture. So there's a claim, which is that, well, if you have this sort of data, like have a sheaf of categories on BG duram, then remember we defined the C as the pullback of F, and the claim is that the monoidal category of D modules on G acts on C. So this is an action in, let me say it another way. So that is D of G acts, nope. C is a module category. Okay, it's faster to do it this way. It's an element of D of G mod of DG cat. Here, D of G is considered as a monoidal, as an algebra in there in the following way. Yeah.
How do you calculate the D of G again?
How did I calculate it in this example? The invariance. So my sheaf of categories is obtained by push forward here. And then the invariants, by definition, are global sections on here. So it's a little bit of a...
This was the definition. It wasn't that we also have a definition for C of G otherwise.
Right, right. So we're going to give a second definition in a second. But there's no other definition right now. OK, so now the fact is that there was a claim, which is that D of G is naturally a monoidal category. By which I really mean an element of algebras of DG cat, like an associative algebra. And the monoidal operation, well, is you take the multiplication map like this, and then we have a map G of G times, well, D of G tensor D of G. It's isomorphic to D of G cross G. And then we have the map of M star de Rham to D of G. And, well, basic formalism easily gives that this sends sort of algebras to algebras. It's monoidal. So since G you can think of as a monoid in the category of schemes, that gives it. So this is some analog of the group algebra in usual representation theory. M star de Rham. So it's like someone gives you two sheaves. I need to tell you how to kind of convolve them in the group algebra. Here's the answer. Take, I mean, it's not such an interesting convolution, but take, F exterior product G on G times G and push it forward along the multiplication map. So for example, if my first sheaf were the delta D module at the identity, my second sheaf would stay as itself by projection formula, I guess. Yes?
The second picture, the claim and claim. Are they?
The second picture isn't given. Oh, OK. Well, let me make a claim. So the claim was, first of all, that D of G acts on C. And the second claim is that this gives an equivalence of categories between G cat and D of G mod of DG cat. In other words, categories acted on by G are the same as modules for the group algebra in this case. So note, this is very different from one affinity of BG de Rham. See, what one affinity would have us do is it would have us take global sections on BG de Rham. And that corresponds to invariance. So global sections on BG de Rham corresponds to invariance. And the claim is that
G de Rham categories.
G de Rham categories is, yeah. I'm forcing it into the notation. There's no, like, it's a perfectly good thing to consider. It's just, yeah. So now the claim is that this functor is not conservative. In other words, well, here it sends some objects to 0 that don't start off as 0.
BG de Rham is not one affine.
BG de Rham is not one affine.
This is the proof.
This is the proof. See, a sheaf of okay, what we're doing is we're saying a sheaf of categories on BG Durham you can really think of as a D of G module category. But the underlying category you obtain by pullback to the point. If instead you took global sections, then you kill off a lot of information.
Which you stated, but not.
Which I've stated but not proved. So I'm going to say the proof out loud because it might, well, Dario will discuss it more. So
you actually have two morphes, like global sections and the other, this one.
Right.
They both arrive at the same place,
Yes.
but only one of them is an isomorphism.
Yes. So what those two functors correspond to, again, you have BG mapping to the point and receiving a map from the point. So one of them is push and one of them is pull. For quasi-coherent sheaves, push corresponds to invariance and pull corresponds to like take the underlying vector space. So in usual representation theory, invariants are not conservative. Here, you can say like an action of the category on a vect is the same as like a character sheaf, like a multiplicative sheaf on the group. And what this will correspond to is like the equivariant category of that. So if your character is non-trivial, you'll get out 0 when you do this. So BGA Durham, for example.
You would still get one affine, right?
If you skip Durham, you do get one affineness. Yeah. So it happens that if you don't do Durham, then you actually, invariants remember everything. It's not a familiar fact from representation theory. So, but let me just state it. Fact BG is one affine. It's not a Morita equivalent. It's a sort of two Morita equivalents between like quasi-co of G considered as a module category, like as a monoidal category. Like modules for that are the same as module categories for rep G, which are what you obtain by taking global sections of quasi-co on BG. So the two are two Morita equivalent. What?
You can call it the one Morita equivalence, right?
Oh, I called it two Morita, but fine. Whatever. Higher, yeah, definitely. So one other just useful, yeah, so how does this example of G acting on X work in this framework? So in the picture of module categories, it works in the following way. So we have a certain action map from G of X cross X to X. And now you can play the same game where you do D of G tensor D of X. That maps actually isomorphically onto D of G cross X. And now you can apply your Durham cohomology to get down to D of X, not M act. So yeah, so this the fact and the claim here that there is an action and that it gives an equivalence of categories, like it's not, well, that there's an action isn't hard. That it gives an equivalence of categories isn't that hard. I'll say something about it in just a second. But it's written in the notes. It's a little technical, and I don't want to do it on the chalkboard. But rather say, like, you'll sort of always know it when you see it. You'll know how to work between these two things. But the fact is a consequence of the one affinity, not of BG Durham, but of G Durham. And actually, you really need G Durham squared, G Durham cubed, etc.
What fact?
This fact. Yeah.
G Durham is one affine by Dennis' theorem because G is a scheme or something, right?
Something like that, yeah. So my GCat by definition, is sheaves of categories on G de Rham, on BG de Rham. That's how I'm defining it. So, OK, there's a lot of complicated terminology around this stuff for distinguishing this point. Oftentimes, people call what I'm discussing a strong action of a group on a category, and an action of quasi-co of G as a weak action of the group on the category. So I'm just dealing with strong actions for simplicity. But
so if you don't take the de Rham, then you get the weak.
yes, exactly. Yeah, all of this goes through verbatim in that case. It's even easier.
Is there a notion of a action of a formal group or a real group?
Of a formal, you mean, yeah, you can take a formal group.
And then this is the action of the Lie algebra, right?
You mean for the strong action?
Well, I'd like to have some notion of a Lie algebra when I get it.
You have a, I mean, you can plug in instead of G the formal completion of G, something like this. And this would be the action, and then what you can say is a strong action is a weak action such that the action of the Lie algebra is trivialized. You've identified it with the trivial action of the group on the category.
In the case of a Lie algebra, a strong action would just be a vector space.
Yeah, it just kills everything, which is no surprise because G hat de Rham is. OK, the conversation's getting a little more technical than I think people can handle, so I think we should move on. So just one other comment. So OK, so we said that if G acts on the category C, then we can form this equivariant category CG. So we can think about that again as global sections. There's actually a second perspective. So you can write this as some huge limit. So of a picture that looks like that was a mistake. It's actually a picture of a huge simplicial, or just as well semi-simplicial diagram like this. And what are the arrows in this? So I'll explain two of these arrows. So the map from C, so I'll explain. So one arrow here is like you go to omega on G, sort of tensor. OK, I'm just going to write omega tensor the identity for C. So this means this is C tensor vect. So this is the functor vect to D of G defined by the dualizing sheaf on G. And the second functor from C to D of G tensor C might be called the co-action map. So in usual representation theory of a finite group, you can think about modules for the Hopf algebra, which is the group algebra. You could just as well think about co-modules for functions on G, which is the dual. So what that's telling you here is, so here the dictionary is that this map is dual to the functor D of G check tensor C to C, where we identify D of G dual. This is dual in the sense of Dennis from yesterday. This is equal to D of G. So the category of D modules on G is self-dual. This requires just a quick word of justification. So Dennis said, well, there's really one setting where you can, one basic setting where you can compute the dual of a category, of a DG category. And that setting is when the category is compactly generated. So you take your compact objects, take the opposite category, and then take ind of it. So what I'm saying is that compact objects of D modules on G or D modules on anything are the compact objects are equal to their own opposite category. And the way you do that is Verdier duality. So one fact is that you can write it as this huge limit. And a second fact is that this canonical functor from CG to C, which we can call, this is Dennis's notation oblivion for a forgetful functor, it admits a right adjoint that's often written av star. So this is the averaging functor. It corresponds to, well, it's the averaging functor, it's right adjoint to oblivion. And first of all, in one example, in the case when g is acting on x, then we know that, so I'm taking d of x to equal c. I know that cg is equal to d of x mod g. This is mapping now to d of x by the pullback functor. So, well, let's say upper shriek pullback functor, and that functor admits a right adjoint. Let's actually say upper star pullback functor. So, I mean, you're a little hard pressed to tell the difference here. And this admits the right adjoint of de Rham push forward. OK, I'm going to call it upper shriek, and it admits the right adjoint of shifted de Rham push forward, because the map is smooth. So for smooth maps, upper shriek and upper star are identified up to cohomological shift by the dimension. And the map from x to x mod g has fibers g, so it's smooth. Yeah? For the right adjoint? Oh, I should actually write continuous right adjoint. Meaning it commutes with arbitrary direct sums.
Are we supposed to justify this formula?
No, they're both just ideas that should sort of be in the background. So I'm tasked with teaching people group actions on categories. So one thing is, like, OK, I want to say, what is this invariance category if you don't know what sheaves of categories are? And this is giving a definition of the invariance category. The second thing is, when you're working with this invariance category, it's really useful to have this right adjoint. So, yes?
In your analogy with group representations of groups, the invariants are actually a subset of the actual thing. So it's like a property to be invariant. And here is an extra data.
So if you were really working with, like, OK, the fact that it's a property is slightly misleading. So if somehow even derivedly, if you did characteristic 0 coefficients, then that would still be true, but in some sense. But
Not if the group is not reductive.
no, for finite groups. But in modular representation theory already, the functor is honestly a derived thing of invariance. So you don't really know what it means to say, like, that whole complex maps as a property.
No, I'm only thinking of the H0, like the.
Yeah, right. So you'll it's just to say it's a misleading analogy. So you can push the analogy a little bit further into other contexts, and it falls apart already in the setting of classical representation theory. So if you dealt with invariance derivedly for a finite group with modular coefficients, you would get into trouble with what you're saying.
Yeah.
It's a coincidence of Naschke's theorem.
But here it is an extra data.
Yeah, it's an extra datum. But OK, so I'll still comment further. So yeah, so this av star operator is the analog of the operator, which is like of the sort of classical operator, which sends a vector v in the representation to the sum of the elements of the group times v. So this is some element of the invariance of a representation. And one way to make that slightly more precise is that you can say it's like, see, this is action by the element of the group algebra, which takes the value 1 on every element of the group. You can similarly say that av star is computed by convolution with the constant sheaf. Kg on G. This is the star pullback from the point. Yeah. So. Yeah.
Would it be okay to call CG like the factorization category?
Yeah, so it's usually called the equivariant category or equivariant derived category. Sometimes a phrase people like. Definitely. Or category of equivariant objects. And so one thing this allows you to see is that, for example, the functor from, so the composition of these two functors. So that if you take an equivariant object, you forget that it was equivariant, and then you average, this is actually going to equal F tensored with the cohomology of G. So one thing that tells you is that if G is a unipotent group, then it's actually a property and not a structure to lie in the equivariant category. But for a reductive group, it is a structure.
How do you see this?
The fact that I'm staying here? Well, let's see it in this example, which is a little easier. So I'm applying pullback and then push forward up to shift. So like pullback from x mod g, push forward. You know that that's given by just tensoring with the push forward of omega upstairs by the projection formula. And then there's the shift. Yeah, so that's what this is encoding. In general, it takes a slight bit of care to get it to work. It's not so serious.
So, sorry, you were saying so if G has no cohomology, then oblivion is fully faithful. Was that the point of that remark?
Yeah, exactly. If G is contractible, which here is unipotent. Other questions? OK, so all right, I think that covers group actions. So next subject on the agenda. Unital categories, there's something else. Oh, rep G is a chiral category. As a factor. I was going to do rep G as a factorization category.
So maybe can you do just arbitrary static order?
Yeah. OK, so how long do I have? 12:15. OK, thank you. OK, so remember that yesterday we said that if A was a commutative K algebra, then that gave rise to some factorization algebra on X, with fibers over X being A. So now I want to give a version of this that's a level up, but will be almost entirely identical. So let C be a symmetric. Maybe it's bad notation. Let M be a symmetric monoidal category. So the claim is that we can produce a factorization category on X out of this. So in fact, OK, so all right, so maybe I'll call this factorization category C. That was our earlier letter for a factorization category. So I need to tell you for each finite set I what C sub x to the I is as a d of x to the I module category. So in the case I is a singleton set, then we're just going to play the same game as before. We just tensor C with d of x. So C is some just like abstract DG category. I'm just tensoring it with d of x. So remember yesterday we tensored our algebra A with omega x. And this plays the same role. You can also think about this in the language of sheaves of categories as pulling back C from the point to x duram. Next, if I is a set with two...
You mean M tensor?
M, yes, absolutely. Thank you.
Yes. No, that's fine.
Okay.
OK, so if if I is the two-element set, then we can play the same game as before. So first we'll do something wrong. So the first thing we would try and do is, well, I'm going to write it in the notation of sheaves of categories. So the first thing we would do is take, well, Cx box times Cx. In other words, we would take, OK, I'll write it in the language of sheaves of categories and then translate that to global sections. So we could start with Cx box times Cx. So this is good because it gives the right answer away from the diagonal. But it's bad because it gives the wrong answer on the diagonal. So what could we do? Well, we could try and correct according to the diagonal. So what we want to say is something like delta star of Cx, mapping here, just to imitate our formula from yesterday. And sorry, delta of C tensor C, well, M tensor M, tensor with, OK, I'll just write sub x to mean tensoring with dx. And then we're going to make this heuristic precise in a second. Too much written, it's illegible. What was that? OK. So the first thing we do is we take M tensor d of x. And then we tensor this with M tensor d of x. No, because I'm thinking in terms of global sections now. So it is tensor instead of exterior product. It seemed. So then I can take M tensor M and tensor this with d of x. And here's my functor from here to here. So I have to give you, well, OK, if I write a formula for it, it'll be too complicated. So I have functors from M here, from M here, and then I have the diagonal push forward functor from d of x to d of x tensor d of x, since that identifies with x cross x. So this is sort of identity on M factors. And delta star duram from d of x to d of x cross x, which I recall is the same category as d of x tensor d of x. And now we have a functor from here to M tensor d of x using the monoidal operation. So I'll just, OK, star tensor identity for d of x. So the operation here is monoidal operation star. And then again, you can form the push out. And this will be our category C sub x squared. So note, everything in sight is actually a d of x squared module category.
So basically on the diagonal, you shrink m tensor m to m.
Yes, using the monoidal operation. So it's exactly the same thing we did yesterday. It's just that when you write it in these terms, it looks more complicated. But it's exactly the same thing that was on this board. The bottom arrow here. So it's written as star. OK, it's probably you can't read it once I write it legibly either. But it's you take the monoidal operation from m tensor m to m, and then you take the identity on this factor. You use that it's symmetric. Like, you need this to be symmetric for it to actually work. See, it's not really like allowed for me to take I to be this ordered set. I'm supposed to do it for any finite set I. And what this is saying is it only depends on the finite set without the given ordering. It's rephrasing the same thing.
Here, you're showing how this existent object looks like. But of course, this is not the way to construct it.
It is not a way to construct it. You can construct it either by being very clever with a nice conceptual technique. You can also just do it through brute force by imitating this construction, thinking what you want, and just doing it over powers of the curve. And yeah, those are your options. So we're going to use this in essentially one case, but I want to make the point that it, like, OK, exercise, work out what it should be over the third power of the curve, and you'll have it figured out. But the point is, like, for the example we're actually going to care about, I can actually construct it in one shot geometrically. So that's part of why we don't need to be too concerned about how this looks over powers of the curve. Yeah? What was that?
You look completely tired.
I'm pretty tired.
So let's, this is enough for what I need in my talk.
Give me 5 more minutes. Yeah. OK, so
Yeah, but I need to survive.
but if I don't survive, I don't have to give any more talks. OK, so the main example is when our symmetric monoidal category is the category of representations of a group G. We'll take it primarily to be G check in the most interesting examples. So here, what we obtain is a factorization category. I goes to rep of G, x to the I. So this is a really important category. So I want to say it's the local version of the category of quasi-coherent sheaves on locus G check, locus G. So again, kind of, if there were a theory of chiral homology here, which there isn't, you would expect it to produce the category of quasi-coherent sheaves on locus out of this category. And for reasons I'll actually will be more clear in just a second. So here's of the category of quasi-coherent sheaves on locus. So in, I don't know what I was going to write. Oh, alternative. Construction that gives it in one shot. So we can consider BG cross X duram as a dx stack, or pre-stack, or space. That was the word I used yesterday. So I can consider it as a dx space. Remember, all that meant was a pre-stack with a map to X duram. So this is certainly a pre-stack with a map to X duram. And
What is this map? So
projection. OK, so it is a pre-stack with a map to X to ROM. So therefore, I can form it was some kind of jets, but I can form, so if I call this y, there was something we called y sub x to ROM to the I over x to ROM to the I. And it gave a factorization space that restricts over x to ROM to give like bg cross x to ROM.
I was going to do this.
OK, well, over x to ROM, it's bg cross x to ROM. So I should say, like, over the second power of the curve already, it's something a little, well, it's infinite type. Like, you won't escape finite type geometry, which isn't so surprising because there were little formal disks around for this whole thing. But it looks so nice over one power of the curve. It's less nice over the second power of the curve. But we have a corresponding category factorization category of quasi-coherent sheaves. This will exactly give rise to this category rep g x to the I. So this is quasi-co of, well, bg cross x to ROM sub x to the I. The version that lives over, or maybe I'll write this to emphasize, it lives over x to ROM to the I.
what? Can you?
Yeah, OK, it's a complicated formula. So here's what I'm saying. So what we want is to produce some version of the particular category rep g that lives over each x to ROM to the I, because we want a factorization category. That means giving a category over x to ROM to the I. So
Either you stop or you explain what you write there in the brackets. So this
I don't know which.
times something with the subscript.
We're having trouble reading
Yeah, so completely ignore this formula because it's cruel. Okay, let me just say it in words. So the problem is we want rep g x to the I. So we want some version of that. How are we going to do it? Observation, rep g is quasi-coherent sheaves on bg. So then if we want to produce some version of bg that lives over each x to ROM to the I, like we want to do it with the physical space first, then we gave a method yesterday. It was something. We gave some definition. And like for any dx space, we produced something that lives over all x to ROM to the i's out of it. And in the particular case, when we apply that to bg, but really it says bg cross x to ROM, because that's the real d space here. In the particular case, when we apply that construction to that d space and take quasi-coherent sheaves, that'll give us our category.
So I don't see what special feature of BG you're using.
None.
Let's postpone because I think everybody's so tired. I think it's not very fruitful. I'll rebuild it. Okay, but this is not a definition. This is required, right? Because the left-hand side you already defined using the fact that this is a only category.
Yeah. So this is a claim, not a definition. Yeah. OK.